We are rapidly approaching a threshold where autonomous artificial intelligence actively breaches network infrastructure. Right now, the tech industry measures this danger using sterile benchmarks. They test language models on isolated capture-the-flag puzzles or have them detect vulnerabilities in static code snippets. A live production system is chaotic. It contains thousands of active nodes, overlapping defense mechanisms, compounding misconfigurations, and legitimate user traffic, creating constant noise. Solving a standalone puzzle in a lab tells us almost nothing about an AI's capacity to navigate the friction and complexity of an actual corporate breach. To measure what these agents can actually execute, researchers at Stanford University set up a massive live-fire experiment. They opened up a university computer science network, encompassing roughly 8,000 hosts across 12 subnets, as the target. They deployed 10 highly certified human penetration testers to compete directly against 6 state-of-the-art AI agent frameworks. Both sides were given the same access and instructed to find and exploit as many vulnerabilities as possible. Standard, off-the-shelf foundation models failed. Frameworks like Claude Code and MAPTA refused to attack entirely, while others stalled out at early reconnaissance, unable to maintain focus over long horizons. The researchers then introduced a custom framework called Artemis. When the engagement ended, Artemis climbed to second place overall on the leaderboard, outperforming 9 out of the 10 human professionals. It achieved this while operating with an 82% valid submission rate. The agent successfully discovered and exploited 9 complex vulnerabilities, including unauthenticated remote code execution, unrestricted directory access, and critical credential exposures granting administrative control. These results provide hard evidence. Properly scaffolded AI agents possess professional-grade offensive capabilities right now. Even the most advanced language models possess deep cybersecurity knowledge, yet they fail multi-day hacks. They lose their place, forget earlier steps, or exhaust computing limits. The solution is scaffolding. Instead of acting alone, Artemis uses a task supervisor to maintain a recursive to-do list and dynamically write custom instructions. This bypasses memory limits, spawning an unlimited swarm of independent subagents to investigate multiple attack vectors simultaneously. This high-volume approach creates a serious problem. Autonomous agents generate massive false positive rates because they misinterpret standard web responses. An agent might read a 200 OK HTTP response and assume it successfully logged in, failing to realize the server actually redirected it to a failure page. To filter the noise, Artemis routes every finding through a dedicated triager module to reproduce and validate the vulnerability. Failed exploits are rejected, and only verified exploits are approved. The danger of offensive AI does not stem from making the underlying module marginally smarter. Instead, it comes from architectural scaffolding that converts a static, simple text generator into a relentless, self-correcting hacking machine. This architecture leads to a stark divergence in how humans and machines operate during a breach. Look at this chart plotting findings over time. Top human performers show a steady upward trajectory. They scan sequentially, validate results, and dig deeper. Contrast that with the AI. Artemis variants experience horizontal gaps of inactivity, interrupted by steep vertical spikes of multiple submissions.
Faster, more urgent tone. This pattern is the result of absolute parallelism. When the AI's main scanner finds an open port, it doesn't stop. It immediately spawns a background subagent to exploit it, while the primary scan continues unabated. In one instance during the Stanford test, a human participant noticed an insecure LDAP server, noted it in their logs, and planned to return later but never did. When Artemis found that same server, it instantly launched 8 parallel subagents to attack the target simultaneously. This speed comes with a fatal flaw. The agent lacks the human intuition to recognize when to dig deeper. It frequently submits a superficial finding, like a misconfigured cookie, and immediately moves on, missing a far more critical code execution vulnerability sitting on the exact same host. A human pentester acts as a sniper, calculating and penetrating deep into a single target. The AI agent acts as an infinitely expanding net, capturing everything on the surface simultaneously. We see which targets favored the human sniper and the AI net in this vulnerability overlap matrix. Focus on the tiny pilot Windows RCE row. 80% of human hackers successfully exploited this critical vulnerability, but the AI columns remain completely blank. AI agents parse data flawlessly via command line interfaces, but they struggle to navigate visual graphical user interfaces, like a remote Windows desktop. While humans simply clicked through the desktop interface to execute the attack, the AI wasted its time running text commands, searching the web for version misconfigurations, and ultimately missing the exploit entirely. This exact limitation becomes an advantage in other scenarios. Every single human failed to exploit an older IRAC server because their modern web browsers visually blocked the connection due to an outdated security certificate. Artemis was unbothered. Unconstrained by a visual browser, the agent passed a terminal command to bypass the SSL certificate verification and exploited the system directly. The AI's current limitations are interface constraints, not intelligence failures. As computer vision agents rapidly improve, this final human advantage in visual navigation will disappear. Beyond technical capabilities, deploying autonomous systems introduces a stark economic reality. The average rate for a human penetration tester is $60 an hour. Netting the Artemis agent costs just $18 an hour. Over a standard year, the human costs $125,000. The AI agent runs continuously for $37,000. AI agents democratize offensive security. Organizations can now run continuous, parallelized red team engagements for the price of a single entry-level employee. These autonomous frameworks are not yet perfect replacements for top-tier human intuition. They do not need to be in order to alter the threat landscape. Their core strengths are simply unmatched. They possess systematic enumeration, infinite patience, and absolute parallelism without any human fatigue. Nation-states and financially motivated threat groups are already adopting these precise architectural efficiencies to scale operations. Enterprise security teams can no longer operate on the assumption that their attackers are limited by human work hours, required sleep schedules, or sequential logic. The enterprise network is no longer a battlefield of human versus human. It is a landscape where absolute automation is the new baseline, and only infinitely scalable AI defense will survive infinitely scalable AI offense.